Ever feel like training a deep learning model is, well, a bit of a shot in the dark?
Oh, absolutely.
You're just sort of fumbling around trying to get it to learn, and it can feel so inefficient sometimes.
Right. But there's actually an engine driving that whole process, these optimization algorithms.
Exactly. The things that guide the learning, making it smarter, more effective.
They're really the brains of the operation. They work to minimize the errors, tweaking the model's parameters, those weights we always talk about.
So that step by step, the model gets better and better.
Precisely. It's all about that fine-tuning.
And that's what we're diving into today. These crucial algorithms. We'll be looking at the big ones: SGD, momentum, AdaGrad, RMSprop, and of course, Adam.
Yeah, and we've got some interesting material, some blog posts explaining the ideas, a research paper doing a proper empirical comparison.
And even a discussion thread, right? Seeing what people grapple with in practice.
Exactly. The goal here is really to help you understand how these things actually work, what they're good at, what they're maybe not so good at.
And crucially, what you should think about when you're picking one for your own project.
We want to cut through some of that complexity, give you those aha moments.
Definitely. We know you want to grasp these things quickly but thoroughly. So, okay, where do we start with all these learning engines?
Well, the logical place is the foundation, right? Gradient descent, GD.
The original.
Pretty much. It's the basic idea that most other methods build on. You're trying to minimize that loss function, the measure of how wrong the model is.
By adjusting the parameters, the weights.
Right. You take little steps downhill, basically, in the direction where the loss decreases fastest, like rolling a ball down a hill trying to find the very bottom.
Okay, always heading downhill. But I remember reading that standard gradient descent is a bit simplistic.
It is, in a way. Standard GD only looks at the first-order derivative. That's basically just the slope of the hill right where you are.
So it doesn't know about the overall shape, the curves.
Exactly. It lacks that awareness of the loss function's curvature.
Which I think brings us to something called Newton's method that tries to understand the curves.
You got it. Newton's method is a second-order technique. It uses something called the Hessian matrix,
Okay.
which captures the second derivatives, how the slope itself is changing, so it understands the curvature.
And that helps it figure out a better step size.
Theoretically, yes. It can make a much more informed guess
Yeah.
about the ideal step to take to get to the minimum faster.
There's always a but, isn't there? Why isn't everyone using it for deep learning then?
The computational cost, that's the killer. Calculating that Hessian matrix is incredibly expensive.
How expensive?
Think on the order of the number of weights squared.
Oof. So for the huge models we use now.
Millions, billions of parameters.
Oh.
It's just completely infeasible. Way too much computation and memory.
So, cool idea, but not practical for deep learning.
Exactly. That's why we stick with first-order methods mostly, but we try to make them smarter.
Right, okay. So back to gradient descent. We understand moving downhill. What about stochastic gradient descent? SGD, that one comes up constantly.
It really does. SGD is a workhorse,
Yeah.
very widely used. It's still quite fundamental, though.
What's the key difference from standard GD?
Instead of calculating the gradient based on the entire dataset for each step,
Which must be slow for big data sets.
hugely slow, SGD calculates the gradient using just one randomly picked data point, or sometimes a small mini batch of points.
Ah, okay. So lots of smaller, maybe noisier steps instead of one big accurate step.
Precisely. And that randomness, that stochasticity, is interesting. It can actually be good.
How so?
Well, that noise can help it jump out of shallow local minima. You know, those little dips that aren't the real bottom of the error landscape.
So the randomness helps exploration.
It can, yeah. But the flip side is that convergence can be slower and maybe a bit erratic, bouncing around more.
And it's sensitive to the learning rate, how big those steps are.
Very sensitive. Choosing that learning rate well is crucial for SGD.
It sounds like trying to navigate with a compass that jumps around a bit. You might get there, but it's not a smooth path.
That's a great analogy. And to smooth things out, we often use SGD with momentum.
Momentum. Okay, what does that add?
It adds a kind of memory, a sense of direction. It accelerates the updates in directions where the gradient has been consistently pointing.
Ah, like giving that wobbly compass some inertia so random bumps don't throw it off course so easily.
Exactly. It keeps track of a moving average of past gradients. This smooths out the oscillations.
Makes it faster.
Often, yes. It helps speed up convergence, especially along shallow gradients, and it's also better at powering through plateaus and escaping those local minima.
Okay, so momentum adds memory and direction. Makes sense. Now, what about these adaptive learning rate methods? That sounds intriguing.
It's a really powerful idea. So instead of one single learning rate for all the parameters, which you either keep fixed or decay according to some schedule,
Right.
adaptive methods adjust the learning rate individually for each parameter during training, based on the history of gradients for that specific parameter.
Oh, okay, so some parameters might learn faster or slower than others.
Exactly. Maybe some weights need big adjustments early on, while others need finer tuning later. Adaptive methods try to figure that out automatically.
Cool. So tell me about AdaGrad. That's one of them.
AdaGrad, yep. Adaptive gradient descent. It was one of the earlier ones. Its main trick is scaling the learning rate for each parameter.
How does it scale it?
It scales it inversely based on the square root of the sum of all the past squared gradients for that parameter.
Whoa. Okay, break that down. If a parameter has had large gradients in the past,
Its learning rate gets smaller.
and if it's had small gradients,
Its learning rate effectively stays larger.
so the idea is if something's been changing a lot, slow it down. Be more careful.
Pretty much. And if something hasn't moved much, give it a bigger push.
Where does that help most?
It's known to work quite well for sparse data. Think like natural language processing, where some words are rare.
Ah, so those rare features get bigger updates.
Exactly. It helps them learn faster, even if they don't appear often.
Clever, but I sense a drawback coming.
You sense correctly. The problem is that sum of squared gradients in the denominator. It just keeps growing and growing.
Forever.
Well, throughout training, yeah. Which means the learning rate for all parameters eventually gets really, really tiny.
So it can just grind to a halt.
It can effectively stop learning prematurely, even if it hasn't found a good solution yet. That's the main issue with AdaGrad.
Right. Starts strong, but fades out. So what came next? RMSprop.
RMSprop, root mean square propagation. It was designed specifically to fix that problem with AdaGrad's decaying learning rate.
How does it do that?
Instead of summing all past squared gradients, RMSprop uses an exponentially decaying moving average of the squared gradients.
Okay, exponentially decaying, meaning it cares more about recent gradients.
Exactly. It gives more weight to recent gradients and gradually forgets the older ones.
So that denominator doesn't just grow indefinitely.
Right. It keeps the learning rate from shrinking too aggressively and dying out. It helps normalize the step size for each parameter.
And that helps with bumpy landscapes.
Yeah, it's particularly good at handling situations where the lost surface has high curvature in some directions, steep valleys. It helps dampen the oscillations.
Does RMSprop have its own knobs to tune? Hyperparameters?
It does. There's usually a decay rate parameter, often called gamma or rho or sometimes mu, that controls how quickly it forgets past gradients, typically around 0.9.
Okay.
And there's also a small epsilon value added to the denominator, just to avoid any division by zero, usually tiny, like 1e8.
Got it. So AdaGrad adapted. RMSprop fixed AdaGrad's decay. Now, the really popular one, Adam.
Adam, yes. Adaptive moment estimation is probably the default choice for many people starting out now.
And why is that? What's its magic?
It basically combines the good ideas from both momentum and RMSprop.
Oh, interesting. So it gets the directionality from momentum.
Right. It keeps track of an exponentially decaying average of past gradients as the first moment.
And the adaptive learning rates from RMSprop.
Yep. It also keeps track of an exponentially decaying average of past squared gradients the second moment, like RMSprop.
And it uses both of those averages.
It uses both to compute an individual adaptive learning rate for each parameter. Gets the best of both worlds, essentially.
And that just works well.
It tends to work very well across a wide range of problems and architectures. It's computationally efficient and often, and this is key, it requires less careful tuning of the initial learning rate compared to, say, SGD.
That's a big plus. Less fiddling.
Definitely. In fact, one of the sources we looked at mentioned their tests showed Adam getting the best accuracy in a pretty reasonable amount of training time.
Okay, so Adam seems like a really strong contender, but the research paper you mentioned dug deeper into comparing these, right? And it wasn't quite so simple.
Exactly. That paper really hammered home one crucial point.
Yeah.
Hyperparameter tuning is everything when you compare optimizers, meaning the ranking you get which optimizer looks best can completely change depending on how much effort you put into tuning the hyperparameters for each optimizer.
So things like the learning rate range you test, the momentum values, how many trials you run.
All of it.
Yeah.
If you just use default settings or only tune one optimizer well and not the others, your comparison isn't really fair or meaningful.
Did they have examples of this?
Yeah, they pointed out that some older studies found Adam might not do as well as finely tuned SGD with momentum in certain cases.
Right.
But this paper argued and showed that if you give Adam the same level of careful, extensive hyperparameter tuning, it often catches up or even surpasses SGD.
So don't blame the optimizer if you haven't tuned it properly.
Yeah, it's a big part of their message, yeah.
They also mentioned something about inclusion relationships. What was that?
Ah, that was interesting. It's the idea that some optimizers are kind of like generalizations of others.
Like how?
Well, think about Adam. It has both momentum and the adaptive scaling.
Yeah.
With the right hyperparameter settings, Adam can almost behave like plain momentum or plain RMSprop.
So it includes the behavior of the simpler ones.
In a sense, yes. It's more flexible.
Yeah.
And their finding was that these more general adaptive methods like Adam, RMSprop, another one called AdamW, when they were all carefully tuned,
Yes.
they never underperformed momentum or basic SGD across the different tasks they tested.
Never. That's quite strong.
It is. It suggests that if you put in the tuning effort, these adaptive methods are consistently powerful. They argued previous studies showing otherwise might just not have done enough tuning for the adaptive ones.
But hang on, what about the no free lunch theorem? Doesn't that say no single algorithm is always best?
Absolutely, and that still holds true. Even if well-tuned Adam is often great, it doesn't mean it's the guaranteed winner for every single problem.
Context matters.
Always. The specific data set, the model architecture, your exact goal. These things can still favor one optimizer over another in specific cases.
Which brings us to the practical side. How do you actually choose an optimizer? That Lightly article had some good advice.
It did. They suggested asking yourself 3 key questions. First, what are people using in state-of-the-art research on similar tasks or data sets to yours?
Stand on the shoulders of giants, basically.
Pretty much. See what's working for others on comparable problems and try to understand why they chose that optimizer.
Makes sense. Question 2.
Look at your data set characteristics. Does anything about your data favor a particular approach?
Like we said with AdaGrad and sparse data.
Exactly. Or maybe you have a massive data set and need to use huge batch sizes for efficiency. Maybe simpler SGD is better for memory in that case.
Right, because the adaptive ones need to store those extra moving averages.
Which takes up memory, yeah.
And the third question.
Your computational resources. How much GPU memory do you have? How much training time can you afford?
Because simpler optimizers might be faster per step.
Generally, yes. SGD has less overhead per update than Adam, for instance. So if you're really constrained, that might be a factor.
The article also had a kind of rule of thumb, didn't it?
Yeah, a useful one, basically.
Yeah.
If you have the time and expertise to really nail down a good learning rate schedule, SGD with momentum is often a very solid, reliable choice. But if you want good results relatively quickly, without spending ages on hypoparameter tuning, especially the learning rate, then adaptive methods like Adam are often a great place to start. They tend to be more robust to the initial learning rate choice.
Okay, so we've talked speed, convergence, tuning, but what about the ultimate goal? How well the model performs on data it's never seen before? Generalization.
Ah, yes, generalization. Crucial. And that research paper had some fascinating, maybe even counterintuitive things to say about SGD versus Adam here.
What was the gist? I thought Adam usually trains faster, so wouldn't it be better?
Not necessarily for generalization, according to their theoretical analysis. It gets into the nature of the noise in the gradient updates.
For randomness in SGD, you mean?
Yes, and even Adam has some noise. They found this noise often has heavy tails.
Heavy tails, meaning?
Occasional, surprisingly large jumps or fluctuations in the gradient estimates.
Okay, and that's good.
Their theory suggests it can be, particularly for SGD. They argue that SGD, partly because of this noisier, heavy tail behavior, might be better at escaping sharp minima in the loss landscape.
Sharp minima, like narrow, steep valleys.
Exactly. And the idea is that these sharp minima might not generalize as well. The model becomes very tuned to the specific training data within that narrow valley.
Whereas SGD, because it's bouncing around more,
might get kicked out of those sharp minima and find flatter, wider minima or basins.
And flatter minima are better for generalization.
That's the prevailing hypothesis. A model in a flat minimum is less sensitive to small changes in the input, like the variations you see in new, unseen data. So it should be more robust.
So SGD's instability could actually lead it to find solutions that generalize better.
That's the argument. They contrast this with Adam. Adam's adaptive scaling, while great for conversion speed, tends to dampen those large gradient fluctuations.
So it might settle into the nearest minimum, sharp or flat, more quickly, but be less likely to get boosted out of a sharp one.
That's the potential trade-off they highlight.
Yeah.
Adam adapts to the geometry, which is great for speed, but might lose some of that exploration capability that helps SGD find flatter regions. They also mentioned batch size. Larger batches can make the training speed difference more pronounced. But the core ideas about tuning and generalization still apply.
Wow. Okay, so it's a really interesting trade-off. Adam often gives you faster training and convenience.
Right, easier to get going, often good results without tons of tuning.
But well-tuned SGD with momentum might, in some cases, find a solution that actually performs better on new data because it's explored more effectively.
That's a key takeaway from that line of research, yes. It really shows that even with all these fancy adaptive methods, understanding the fundamentals of SGD and its variants is still incredibly important.
Well, this has been quite the journey through these optimization algorithms. Really fascinating stuff.
We've covered a lot of ground, haven't we? From basic gradient descent.
Right, through SGD, adding momentum.
Then into the adaptive world. AdaGrad for sparsity, RMSprop fixing the decay.
And Adam bringing it all together, plus the whole tuning aspect.
And finally, thinking about not just training speed, but that crucial generalization performance.
And the big message seems to be, you really need to think about your specific situation, your data, your resources.
And definitely the hyperparameter tuning. Can't stress that enough.
It's clear there's no single best optimizer that rules them all.
Nope. It's context dependent. Experimentation is often required.
So maybe a final thought for everyone listening. While adaptive methods like Adam offer fantastic convenience and often great performance,
Don't completely write off SGD, especially SGD with momentum.
understanding how it works and how its noisy nature might actually help find more generalizable solutions in some cases. That's valuable.
It might be worth the extra tuning effort sometimes. So definitely keep exploring, check out recent research, and most importantly, try different things on your own projects.
Yeah, get hands-on. This deep dive gives you a strong foundation, but there's always more learning rate schedules, batch sizes, newer algorithms.
The field is always moving. But hopefully this gives you a much clearer picture of the optimizers driving deep learning today.